Okay, well, it's a pleasure. Thank you very much for being here. For the next 50 minutes, I'll be talking, no, I'm kidding. For the next 20 minutes, I'll be talking about three topics, actually. But let me start by thanking Professor Brown, Professor Bagnato, Professor Phillips, who were people who signed the invitation that I received, as well as Cardinal Turkson, Sister Maca, and all the staff that have made this magnificent event possible. So I thank you very much for that. Also thank the university I work for, Tecnológico Monterrey, and in fact, this is the first topic that I would like to quickly address, which is the institution I work for, and this is because several of you have actually been kind enough to ask where I work. So this is where I work. It's a university with 90,000 students in Mexico, 28 campi. It's spread all over the country. We do a lot of engineering, applied sciences, chemistry, applied mathematics, etc. We have 3 hubs, which are devoted to data science, cybersecurity, and artificial intelligence. And we also have a number of different PhD programs. So that's basically what I do. And that's important to say it because you see the Spanish-speaking world, in particular the Latin American subcontinent, is pretty much unknown in the English-speaking world. So getting closer and getting to know each other, partly is to know what we do in each part of the world. We have several alliances, in particular with the MIT and other universities worldwide, and that's it for the university I work for. This is my group. We work on a number of subjects. We founded quantum computing in Mexico, and we work basically on quantum algorithms and quantum cybersecurity. Now, the topics I would like to address in this talk, the first one, well, in the beginning, my talk was designed to talk about the actual topic of the workshop, which was whether to answer or try to answer the question as to whether it would be an increase or decrease of technological and social gaps with the advent of quantum technology and quantum science. But then I realized that many of you were talking about your research, so I'll be talking briefly about the research we do in my group, and then I'll address the second topic. And right now I'm going to talk about research field we've been working on for the last 3 years, which are entitled Quantum Walks over Genotype Networks. Basically, the idea here is this goal, to explore genotype networks using quantum walks, in particular continuous quantum walks, possibly in order to possibly identify potential advantages with respect to exploration of the same networks via classical random walks. And the long-term goal is the one that we have there. So this topic is basically the very first step towards trying to answer the questions that come up with those goals, which is to assess new ideas from the field of biology, for example, quantum biology or quantum effects in mutations and adaptive mutation, as well as to produce new computational tools to study biological data and processes. I don't know, and I think that no one on Earth knows, whether biology is quantum or not. I don't know exactly what are the quantum mechanical effects that we should take into account in order to have better biological models. But I know that quantum computation can become a very important tool for providing new elements, new ways to understand biology. Because a striking difference between biology and other branches of science like physics is that in physics as well as in computer science, to a certain degree, we can actually start with toy models, and out of those toy models, we're going to start growing up building more elaborate and complex models. This is not the case in biology at all. The very simple, the simplest mathematical models of the simplest phenomena in biology happens to be extremely complex. And in my opinion, in fact, there is a severe lack of understanding and a lack of mathematics in order to address those problems, to properly model them from the very beginning. So I think that quantum computation could become, who knows whether it's going to be a quantum algorithm for describing, for example, the process of a mutation. But we can certainly use it to find out, to elaborate more, to get to know more about the fundamental structures of biological systems and of life. So that's the long-term goal. These are some definitions that are needed in order to understand the following topics, which is the definition of a genotype is basically the genetic constitution of each one of us, of each living organism. A genotype space is the mathematical space in which all genotypes live, and phenotypes are basically the the embodiment, the body expression of the interaction between genotypes and the environment. And finally, connection between genotypes in this sense is by a mutation. So there are two genotypes connected, it's because there's a mutation between two individuals. And finally, a genotype network is the connected set of all genotypes in a genotype space that have the same phenotype. So basically, all the mutations that happen in a species that have only one or none, say, observable effects. Okay? And the goal that we've been, the very first goal that we've been trying to achieve, the first thing we wanted to understand by running both classical and quantum walks over genotype networks and connections of genotype networks is how fast we can actually reach a new genotype, a new phenotype. Right? So these are the mathematics of the problem that most of you surely are very familiar with. We built a continuous quantum walk for that. And the reason for using continuous quantum walks instead of discrete quantum walks is the mutation rate. The way that basically that biological mutations happen is, actually we ended up publishing a paper on that. How, I mean, more accurate than what existed before, a more accurate model of how exactly these jumps in time happen in mutations. So we ended up finding out that it could be described by a Poisson process, and so that's information which is contained in the gamma parameter. Okay? So basically, we produce a Hamiltonian, and that Hamiltonian is run as a continuous quantum walk. What have we found? And over the same genotype networks, we ran both classical random walks and continuous quantum walks. What we found, what we wanted to do was to identify which walk is more efficient at finding new phenotypes. So we found that in the first paper that we published, the simulation results showed that for two phenotype networks, meaning only two phenotype networks connected, there was a similar performance for both classical random walks and quantum walks. Now, when we increase the number of phenotype networks, that is when we had 3 or 4, then the continuous quantum walks perform better. Now, these two are toy models, because one of the things that we should ask now is how exactly we run quantum walks, because there is no hardware for running quantum walks nowadays. So there are two options. The first one is to translate the quantum walk-based algorithms that we have onto the quantum circuit model, which is an extremely difficult problem. We know that both models are universal models of computation, but no one knows how to make those translations, I mean, the translation from quantum walks to quantum circuits and vice versa, efficiently for arbitrary cases in general. So that's actually a topic that we've been working on in my group for a number of years now. But then it was either that or running simulations, digital simulations of quantum walks in digital computers. So that's what we did with this first paper. Okay? We used a server, quite a big enough server for that. But it was only for only 4 genotype networks. Then, of course, the next step was we need to increase the number of genotype networks to use. Okay, we want to have more genotypes, and therefore we need way more powerful systems. So we used HPC systems, high performance computer systems, that were gladly the access to these systems was gladly granted by IBM. So we thank them from the bottom of my heart for that, because otherwise it would have been really impossible to run the simulations for this second step of our research. So we did, I mean, basically what we did was we increased the number of genotype networks. We run over the same rationale, both quantum walks and classical random walks. As I said, we found a new way to define the notion of hidden time in continuous quantum walks based on the definition of a Poisson process. And this is what we found. With digital equipment simulators, we found over 3 different genotype spaces, one for a flower, another one for a mushroom, and finally for the mouse, for the mouse, or for house mouse. We found that the heating time for quantum walks happens to be shorter than the corresponding classical heating time, and the relationship is the one that we have there. Classical over quantum is approximately equal to 175. So 175x faster quantum than classical. And as I said, we received a grant from IBM that we very gladly used it, and thanks to that, we have this result. Now, the third and final step, which is what we're working on now, is to explore the effects of radiation and temperature on gene mutations in open systems, because both the two previous steps were run using Hamiltonians over the Schrödinger equation. That is to say, another way to pose the unitary evolution. But it happens that the DNA is exposed to the environment and to the effects of radiation and many other things. So the next step is to have a way more complex mathematical model of mutations, taking into account the effects of the environment. So that's what we're working on now. This is briefly the description of the Hamiltonian that we're using that takes into account the structure of the DNA, internal effects, indirect effects, as well as radiation and temperature and blah, blah, many other things. So what are we going to find here? Still don't know. We'll let you know when we publish the paper. Okay? So that's it for the research that we've been working on. How long do I still have? Thank you very much. Okay, now I'll briefly talk about what we've been doing in Mexico in quantum technologies. The link to the main document, well, if you want, I can, of course, share the slides, and then you will find the main document. But a few examples of the things that we've been working on the development of quantum technology, that is to say, in addition to the basic science research that we run in Mexico, is portable quantum gravimeters. This is a key research product in Mexico for, well, basically Mexico City, as you may know, we are expecting Godzilla to arrive in a few years' time. And this is because we have earthquakes. We have a volcano, an active volcano just next to the Popocatépetl. So we have serious trouble with natural disasters. And then producing gravimeters so that we can have more accurate models of the natural disasters that potentially have an impact in Mexico City and other parts of Mexico is an important thing to us. So this is a TRL4 development that we've been working on over the last few years. Another example, is quantum optics-based tomography, TRL3, by a good friend of mine, Professor Alfred Uren. And finally, quantum cryptography, which is kind of the jewel of the crown in terms of the TRL level that we've been developing in Mexico. It's a full laboratory very near Mexico City that is devoted to a number of technologies related to quantum cryptography, BB84, E91, so on and so on. Okay, now the title of this workshop is Increasing or Decreasing, or subtitle, Increasing or Decreasing the Technology and Social Gap Between Nations. So actually the paper I wrote for this workshop is basically a combination, it's a selection, of reflections and considerations about two topics that run in parallel. One of them is the basic components of a roadmap that we are working on back in the university I work for with the business school in order to be able to identify the crucial steps and times that we would expect for different quantum technologies to become part of the economic engine of each nation, particularly ours. And also the role that nations with, let me say it this way, with a limited amount of access to human capital and financial resources can do in terms of being part of the quantum technology market or ecosystem. So as I said, this is a work that has been done in collaboration with the Business School Tecnológico de Monterrey. And well, this is kind of the basic hypothesis. The successful deployment and commercialization of quantum-based products and services is going to be a very complex and long-term endeavor and will require, in addition to basic and applied research, the development of high-tech tools for engineers and technicians devoted to production, innovative teaching methods, continuous identification of new applications, industrial standards, and novel business models. So basically, I mean, of course, the basic research that we all do is fundamental for the advancement of quantum information science and quantum technology. But in order to make quantum technology part of our economies, there's also a very long road to be walked that basically has to do with providing with tools that engineers like me need in order to build products, to build services, and then, thank you very much, and then, well, to have industrial standards and novel business models. So I have 5 minutes left, so I'll briefly talk about 3 topics. The first one is the Quantum National Initiative. Many countries like the United States, the United Kingdom, actually a region, the European continent, have national quantum national initiatives. And there was a question posed at the World Economic Forum meeting on the Quantum Economy Network last 2 weeks ago, which was whether it would be sensible or pertinent for every country on Earth, or most countries on Earth, to have a quantum national initiative. There are, of course, different answers to that. My answer is that countries that want to increase their economic power, their economic growth, need to find new ways, new paths, in order to make full use, to maximize the benefits of the human capital and the access, whether modest or very modest or whatever it is, to financial resources. A good example is actually Mexico. Mexico used to be a provider of raw material for many years, and we transformed our economy, and we became a manufacturing society. So our economy is basically 70% of it, or 50%, sorry, is produced out of manufacturing. It can be, for example, we produce most of the cars that are sold in the American continent. We are the second largest commercial partner of the United States, and we're just about to become the first. And this is because of the manufacturing that we run in Mexico. So the thing is that, in my opinion, the development of quantum national initiatives is not a matter of whether, but a matter of how and when, taking into account, of course, the capacities of each country and the access that they could have to financial resources. That's one thing. The second topic I would like to address, and this is for those of you who are interested in education, I would really like to listen to your opinions, is what we have to do in order to educate or to train the quantum workforce. And this is, first of all, because it is a really heterogeneous group in which we're going to find, of course, the students who go for BScs, MScs, PhDs, but we're also going to have seasoned scientists and engineers who are working in industry, in other branches of industry, and who want to have either a career switch, a career move. They want to get into the quantum information and quantum technology business. They need training, but the training that they need is different in principle. And what I mean by that is in nature and in topics to the training or the education that could be provided in full-time programs like PhDs or Master in Science. We also have professionals and students from fields which are say, hard science related, like economics, business, politics, who need to understand some fundamental facts about science, quantum information science, and quantum technology. And that the thing is that, I mean, these people are key, are crucial, are fundamental in order to advance the field. Why? Because having a politician understand the basis of what we do, not necessarily what happens in a laboratory, but the potential effects and benefits of quantum technology, we need them to understand that so that they can push the agenda where the agenda has to be pushed. Okay? And the same happens with business people, so on and so forth. And they need training, as well as entrepreneurs. So here I would say that lessons from the past are very important. I'm an entrepreneur. I own a company of solar energy systems. And what I found in terms of education of people who are interested, who have been interested over the last 15 years in solar systems, is a scenario which is quite close to what we're going to have in quantum information science. Having people from different fields, from heterogeneous backgrounds, interested in learning about selected topics of this field. So we can use that. And whatever we do for education, we need to take into account what I call here the new learning styles. Young people, and this is something, I mean, life begins at 8, right? So we all are still young. But the people we train are much younger. And the habits that they have, the way they interact with the world, is very different from the way we do it, from the expectations and the assumptions that we have. So the question here is, what can we do in order to design educational methods, educational tools that use technology and also take into account the actual, what I call learning styles, that we could also call learning preferences, whatever it is, but that can have a beneficial impact in our students. And I have 1 minute, so I'll skip that. I'll skip that one. I was going to say that we need to develop tools, very good tools for engineers and technicians to work on quantum information science and technology. Okay, and these are the collaborators that I've been working on for the ideas that I have introduced in this talk. And thank you very much indeed for your kind attention.